Hi everyone. In the last few lectures, we have discussed about the spectral measure and the relation between spectral measure and representation of B of x into B of h. In particular, we have shown that if x is a compact space and rho is a representation from B of x into B of h, where B of x denotes the set of all bounded Borel functions taking values in C, then there exists a spectral measure E such that rho is represented by the spectral measure E. That means rho of f is integral over x f dE. On the other hand, if E is a spectral measure on x omega h, where x is a compact space, omega is the Borel sigma algebra of x, and h is a input space, then associated to this spectral measure, we have shown that there exists a representation from B of x into B of h such that rho of f is integration over x f dE. That means there is a relation between spectral measures and representation. Now today we are going to uh, apply these results to bounded normal operators. So let us start with a bounded normal operator T. And if you take a continuous function on spectrum of T taking values in C, that means it's a complex valued function defined on the spectrum of T, then we have defined that f of T is nothing but limit of Pn of T, T star where Pn is a sequence of polynomials in two variables z and z bar. And we also have shown that f of t does not depend on the approximating polynomial Pn. It is independent of the sequence of polynomials. Now if you look at a map, so this gives a representation from C of sigma of t. So here we always consider the functions are defined on spectrum of t and they take values in C. So here we don't need to take this one. So this gives a representation from set of all continuous functions on spectrum of t into B of h, which sends f into corresponding f of t. So in fact we can show that this is a representation. Okay, let us see how to get this representation before applying the earlier result that we have got. So let us look at let A to be the C star algebra generated by the identity operator on H and T. So this is a commutative C star algebra, commutative unital C star algebra. So if you look at the Gelfand map from A into C of MA, where MA is the maximum ideal space, it is defined by gamma A at phi, where phi is coming from M suffix A. This is phi of A for every phi in MA. So here MA is set of all functionals from A into C such that phi is linear and multiplicative. Of course phi is non-zero we can show that phi is bounded and norm phi equal to 1. Okay. Now this gamma is a representation from A into C of MA, and from C of MA we want to have a representation from C of spectrum of T into B of H. Now if you look at, so we can actually get a homomorphism from MA. Let us say tau is a map from MA into spectrum of T. So define by tau of phi is nothing but phi of T, and phi is a functional from A into C, and in fact here A is nothing but the C star algebra generated by I and T. So this is nothing but we can say that this is exactly equal to span closure of all polynomials in T star, where P is a polynomial in two variables Z and Z bar. Okay. Now we can show that if you take phi from MA, phi of T is element of spectrum of T. Now with this map we can in fact give a association or correspondence from C of MA into C of spectrum of T. So in fact we can show that this is a homeomorphism. Now with this we can get a representation C of M from C of MA into C of spectrum of T. So let us call this as eta. This is the representation. So if you take F here, F going to F composition tau, so this will give a representation from C of MA into C of spectrum of T. Now we have the map gamma from A into C of MA, and now from C of MA into C of spectrum of T we have eta. If you look at eta composition gamma, it's a map from A into C of spectrum of T. This is a representation. Actually we want to get a representation from C of spectrum of T into A. So if you look at, let us take rho as eta composition with gamma inverse, this is a map from C of spectrum of T into A. Now this is a representation. So we got a representation from C of spectrum of T into A. In fact, now A is a C star algebra generated by the operator I and T. Since T is normal, this is a commutative C star algebra. So we can actually treat this as subalgebra of B of H, because it is in fact a subalgebra of B of H. So we got a representation rho from C of spectrum of T into B of H. So in fact, as we told earlier, rho of F we can define as F of T. So this is called continuous functional calculus for T. We know that by Weierstrass theorem, polynomials in two variables Z and Z bar is uniformly dense in C of spectrum of T. And on the right hand side, for the C star algebra A, we know that the polynomials in T and T star is dense in A on the right hand side. If you look at polynomials in Z and Z bar, this is mapped to polynomials in T and T star. If you look at the function f of Z equal to Z, where Z is coming from spectrum of T. This is mapped to the operator T. And if you look at F bar is mapped to the operator T star. So in this way we can get a representation from C of spectrum of T into B of H. Now we can apply the earlier result that we have proved. So given any representation, we can get a unique spectral measure where this representation is represented by the spectral measure. So by the earlier result, there exists a unique spectral measure E on spectrum of T is a compact set. Omega is the Borel sigma algebra of members of spectrum of T, and H is a Hilbert space, such that F of T equal to rho of F, that is nothing but integral over spectrum of T F d, or we can write this as F of T is nothing but integral over spectrum of T F of Z dEz for every F in C of spectrum of T. Okay. Now we also have seen that we can extend this rho to B of X. So let us take rho hat from B of spectrum of T into B of H be the extension of rho. So that means rho hat restricted to C of spectrum of T is nothing but rho, and in fact rho hat of G is nothing but integral over spectrum of T G dE for every G in B of spectrum of T, where G is a bounded Borel function. Okay, so let us look at a particular case. In particular, if we take F of Z equal to Z, we can actually get representation for T, that is integral over spectrum of T Z d, and we can easily show that T star is given by integral over spectrum of T Z bar d. Let us state and prove the spectral theorem. Let T be a bounded normal operator, then there exists unique spectral measure on spectrum of T omega H. Omega is the sigma algebra of subsets of spectrum of T. In fact, it's a Borel sigma algebra of subsets of spectrum of T such that f of T is integral over spectrum of T f d for every f in C of spectrum of T. So if you want to write if and G are coming from H, then we can write the same as inner product f of T G with H is integral over spectrum of T f d e g h. We know that e suffix gh is a complex measure. Okay, this is the spectral theorem, and apart from this can also get the following. We can get that if G is a non-empty open relative open subset of spectrum of T, then we can show that E of G is non-zero. The second part is, let us take A to be a bounded operator, then we can say that AT equal to TA and AT star equals to T star A if and only if AE delta equals to E of delta A for every Borel subset delta of spectrum of T. Okay, we have already proved the first part. Now we want to look at the results A and B. To look at the proof. Okay, so let G be a non-empty relative open subset of spectrum of T. Let okay, so we can choose a continuous function. Let f from spectrum of T into C be a continuous function. Such that 0 less than f less than chi of G. In fact, we can choose a non-zero continuous function with this property. In fact, we can do this by applying Urysohn's lemma. So let us take Z in Z, apply Urysohn's lemma to the sets the singleton Z and G complement intersection spectrum of T to get such a function. Now we know that rho hat is a representation. So as rho hat is a representation, and it also preserves the involution. So we can, because it's a star homomorphism, we can conclude that rho hat is positive. So it preserves the ordering of elements. So 0 less than rho hat of f less than rho hat of chi g, but we know that rho hat of chi g is nothing but E of g, and we also know that rho hat is isometry. So when f is non-zero, we know that this is also non-zero. So from this we can conclude that E of g is a non-zero projection. Okay, so this completes the proof of A. So let us look at the proof of B. Okay, so let us take A is in B of H such that AT equal to TA and AT star equal to T star. So from this we can conclude that this implies that A P of T star is P of T star into A, where P is a polynomial in Z and Z bar. Now, using the continuous functional calculus, we can say that A of rho f is nothing but rho f into A. So that means A f of t equal to f of t A for every continuous function f. Okay. Now let us look at the following set. So define omega tilde as set of all sets, Borel sets, delta in omega, where omega is the Borel sigma algebra of subsets of spectrum of T. So this delta has a property that TE delta is E delta into T. Now we know that E of empty set is 0, E of the full set spectrum of T is identity. So from this we can conclude that empty set and the full set spectrum of T are inside omega tilde, and we know that omega tilde is a subset of omega by definition. So our claim is that omega tilde is exactly equal to omega. So to prove this, we want to show that if G is any open set, we want to show that G is also inside omega tilde. So from that we can say that omega is contained in omega tilde, because omega is generated by open sets. So let us take G be a non-empty open set, relatively open set. Then we know that E of G is non-zero projection by A. So our claim is that T of Eg equal to Eg into T. So to show TEG is nothing but Eg into T. If you look at this at the representation level, so it is, if you take, let us take f of z equal to z for every z in the spectrum of T. We know that E of G is nothing but rho hat chi suffix G. So we also know that f commutes with chi G Hence by applying rho hat, so rho hat f chi g equal to rho hat chi g f, or we can say that rho hat f rho hat chi g equals to rho hat chi g into rho hat f, because rho hat is a representation. So this implies t into Eg equals to Eg into t. Okay, from this we can say that our claim is proved, that omega tilde equal to omega. Okay, now what we want to show is, we want to show that A commutes with E delta. So let us choose a sequence Fn of continuous functions on spectrum of T such that 0 less than or equal to Fn less than or equal to chi g, and not only that, Fn increases to chi g. Okay, now we want to look at, so let us take two elements G and H in H. Then let us look at, we want to show that A Eg acting on G inner product with H. So our idea is that we want to look at open sets first. So let us take an open set. Let G be a relatively open set. In spectrum of T. So we show that A commutes with Eg. From that we can conclude that A commutes with E delta for all Borel sets delta. So this we can write as inner product Eg acting on G with A star H. And this is nothing but, Eg is nothing but rho hat chi g acting on G inner product with A star H, but rho hat is given by the integral over spectrum of T chi g dEg A star H. So that is nothing but, we will get this as integral over spectrum of T chi g dEg A star H. This is nothing but integral over spectrum of T limit Fn dEg A star H. We can take this limit out. So this is limit over spectrum of, limit n tends to infinity, integral over spectrum of T Fn dEg A star H. So this is nothing but integral over spectrum of T Fn is nothing but Fn of T. So this is limit Fn T and inner product with this element with A star H. Okay, so this is nothing but limit A Fn T acting on G inner product with H. But we know that a of f of t commutes a of f of t equal to f of t into a, that we have already observed. Yes. So we have shown that a into f of t is f of t into a for every continuous function. Since each fn is continuous, we can use this property here. This is limit fnt ag h. So this is nothing but limit integral over spectrum of t fn d agh. Again we can take the limit inside. This is integral over spectrum of t. This is chi g d agh, and this is nothing but inner product e of g ag with h by definition. So we have shown that this quantity equals to this one. So from this we can conclude that aeg is eg into a for all relative open subsets of spectrum of t. So this implies that e delta is e delta a for all Borel subsets of spectrum of t. Okay, so this completes the proof of 2 in one direction. So we have to look at the other direction. Suppose a commutes with e delta for all delta. We want to show that a commutes with t as well as t star. So conversely, so assume that a e delta is nothing but e delta into a for all Borel subsets of spectrum of t. So from this we can write a rho hat chi delta is nothing but rho hat chi delta into a. Chi delta is a characteristic function. Since rho hat is linear, we can show that the equality holds true for simple functions also. Now when we have a bounded Borel measurable function, we can approximate it by a sequence of simple functions, simple measurable functions. So from this we can conclude that so in particular if we take f of z is z for every z in spectrum of t, then we can say that at equal to ta. So if you take g of z equal to z bar, then you will get a t star equal to t star a. Then we can get a t star equals to t star a. Okay. So this completes the proof of second statement. So in this proof we have shown that for a normal operator t, so let me write as a remark. So we have shown t e delta equals to E delta into T for every Borel subset delta of spectrum of T. And we have shown that if T is self-adjoint and if A commutes with T, then the spectral family generated by T also commutes with A. So here also we can prove the result with slight difficult way, because when T is self-adjoint, so the conditions here are automatically satisfied. That means whenever A commutes with T, then automatically A commutes with T star. But in the normal case, we have to do little bit more work. So we can actually show that if A commutes with T, then we can show that to A for all Borel subsets delta of spectrum of T. Okay. Now using this result 2, we can actually show that we can actually strengthen the second statement B here. That means we can show that if A is a bounded operator such that AT equal to TA, then AE delta equal to E delta into A, and the converse is also true. That means we can actually drop one of these two conditions to get the conclusion. Okay. Let T be a normal operator which is bounded, and A is a bounded operator on H such that A commutes with T, then we can show that A commutes with T star also. Okay, so let us look at the spectral measure for E. Let E be the spectral measure. For spectrum of T omega H. Let us take vectors G and H from H. Then we can look at inner product A T star acting on G with H. So this is nothing but T star G inner product with A star H. Now we can use the spectral representation of T. So we know that T equal to ZDE over spectrum of T, or we can say that Tg at H is integral over spectrum of T Z DEGH. Now if you look at T star is nothing but integral over spectrum of T Z bar DE. Now we can using this representation for T and T star, we can write down T star G inner product A star H. So this is nothing but integral over spectrum of T Z bar D E G comma A star H. Now this can be written as integral over spectrum of T Z bar. We can show that this is nothing but D E A G H just by looking at the definition of EG A star H. So we have This is nothing but inner product E delta G A star H, and this is nothing but A E delta acting on the inner product with H. But we know that A commutes with T, then A commutes with spectral projections of T. So this is nothing but E delta A G H. So this is E A G H acting on delta. Okay, so this is again we can write nothing, this can be written as inner product of T star AG with H. Now from this we can actually conclude that A T star equals to T star A. Okay, so this completes the proof of Fugler theorem. So there is one more generalization of this result, Fugler theorem. It is known as Fugler-Putnam theorem, or it is also known as Putnam's corollary. Let A and C are bounded operators on H, both are normal, and B be a bounded operator on H such that A be equal to BC. Then we can say that A star B equals to BC star. To prove this result, we actually use the earlier result, which is the Putnam's result. So prove. So let us write down T as A0 0 C and S as 0 B 0 0. So these two operators are defined on H direct sum H. They are bounded, and in fact we can show that T is normal. And we can say that S is bounded on H direct sum H. With the given hypothesis, we can show that St equal to Ts. So let us consider St, that is nothing but 0 B 0 0 A 0 0 C. This is nothing but 0 BC 0 0. And if you look at Ts, A0 0 C 0 B 0 0. So this is nothing but 0 AB 0 and 0. Now we know that AB equal to BC by the hypothesis. We can, so AB equal to BC implies ST equal to TS, and it is clear that T is normal because it's a direct sum of two normal operators. So by the Fugler theorem, so we can say that S commutes with T star, so that ST star is T star S. So that means we can say that if you look at ST star 0 B 0 0, this is A star 0 0 C star is equals to 0 B C star 0 0, and if you look at T star S, this is nothing but A star 0 0 C star so this is nothing but 0 A star B 0 0. Now S T star equal to T star S, so this condition implies that these two entries are same, that is, so therefore BC star A star B equal to BC star. So we wanted to show that only, A star B equal to BC star. So this is known as the Putnam's corollary. Okay. Now let us look at one more important result for the multiplication operator. So let us start with x omega mu sigma finite measure space, and let us take phi from L infinity of mu. So we can define the multiplication operator. Define m phi from L2 of mu into L2 of mu by m phi at f is nothing but phi into f for every f in L2 of mu. So we know that this is a bounded linear operator. So we already proved these results. M phi is bounded with norm of m phi is essential supreme of phi. M phi star is exactly m phi bar, and m phi is normal all the time. And spectrum of m phi is nothing but essential range of phi. So these results we have already discussed earlier. Now we want to look at spectral measure for m phi and how to look at functions of m phi. Okay, so here earlier we have seen if phi is coming from L infinity of mu, then we can define a spectral measure. So E delta we can define as the multiplication operator induced by the characteristic function supported on phi inverse of delta, where delta is a Borel subset of spectrum of m phi. Okay, so if we take function psi, which is a bounded Borel function defined on spectrum of m phi, then we can again show that psi of m phi, this is again a normal operator, and in fact we can show that this is a multiplication operator. This is multiplication induced by the function psi composition phi. So here the idea is first we take psi to be a simple function, then first we have to take psi to be a characteristic function, then simple function, then approximate given bounded Borel function using simple functions. So it is enough to show this result for simple functions or even characteristic function, so then we can get the result. Similarly, to show the this E delta gives a spectral measure, it is the usual method. by looking at the properties of characteristic functions, we can show that uh, it forms a spectral measure for M phi. Using this, we can actually uh, write down the integral form for M phi. Okay. So this is information about spectral theorem for normal operators. Earlier we have shown that spectral theorem for normal operator, which is a multiplication form, that is nothing but every uh, normal operator defined on Hilbert space H is unitary equivalent to a multiplication operator induced by a function phi on spectrum of T. Okay, so this is another version. In fact, uh, there is a relation between the multiplication form and integral form. One can assume multiplication form and go to the integral form, and one can assume the integral form and go to the multiplication form. So we will stop here. Before concluding this lecture, in fact the course, I would like to thank the following people: Miss Shanola Smita and Miss Bhumi Amun. Uh, they are my PhD students who supported in verifying the content and recording the videos. I am very much thankful to them. I also thank my parent institute, IIT Hyderabad, for supporting uh, for recording these lectures. And finally, I would like to thank NPTEL team at IIT Madras for giving me this opportunity to record these lectures. And if you have any comments and suggestions regarding the course content as well as videos, I request you to write to the mentioned email ID. Once again, thank you very much.